Hi everyone, Jonathan here. This video is going to be my take on the intuitive definition of the limit of a function. In this rather long section, the book gives the definition of several different types of limits. The first is the two-sided limit, which is basically the plain limit without any extra adjectives. And it says the limit as x goes to a of a function f of x equals L basically means that f of x gets really close to L as x gets close to a. Next, the function defines one-sided limit. This here is a limit from the left, and this means that f of x gets close to L when x is close to a but slightly smaller, whereas the right-hand sided limit here says that f of x gets close to L when x is close to a but larger than a. The book also defines infinite limits. So the limit of a function is infinity when the function gets arbitrarily large, when x is close to a. And I don't know if the book defines these explicitly or not, but you can also have one-sided infinite limits. For example, the function might get arbitrarily large when x is slightly smaller but close to a, and f of x might do something else when f of x is near but slightly larger than a. But what does this all mean? There's a bunch of different types of limits. How should you think about limits? In every single case, a limit is telling you the behavior of a function near a point. I'm going to demonstrate that for you with some graphs. Here we're looking at the graph of f of x equals x cubed minus x over x plus 1. And the question is, what's the behavior of f near the point x equals minus 1? So you can take the limit of any old function at any old point, but it turns out that limits are only interesting at points that either aren't in the domain of the function. Notice if you try and calculate f of minus 1, you would get 0 in the bottom of a fraction here, so minus 1 is not in the domain. Or at least something else interesting is going to be happening around that point. To investigate the behavior of f near minus 1, I made this slider here, which allows you to see what happens to an input a, and what's the corresponding output f of a going to be. And you can make a be closer and closer to minus 1. So for example, when a is minus 0.5, we get f of a as 0.75. So I'll move a closer and closer to minus 1, and notice that the values f of a are increasing. They're at 1.8 right now, and if I move it even closer, the closest I can make it is a equals minus 0.99, and we get f of a to be 1.97, and you'll notice it's very close to the number 2. F of minus 1 is undefined, which it says so that's nice to see. And on the other hand, if I approach from the other side, so as I move a closer and closer to the right, let's see, we're getting at 2.8, 2.6, 2.4, and let's see how close I can get it. When a is minus 1.01, it's kind of hard for me to, it's a bit fiddly. Well, we'll settle for minus 1.02. We get the f of a is 2.06. In all cases, it seems that the function is getting very close to 2. And if I could make a get even closer, say minus 1.00001, then we'd see the f of a would be even closer to 2. So in this case, we say that the limit as x goes to minus 1 of f of x is equal to 2. The reason for that is the behavior of f when x is very close to minus 1 is that f of x is very close to 2. Now we've got another function, g of x equals x squared over 4 times the quantity of x minus 2. And the question is, what is the behavior of g near x equals 2? So you can tell from the graph, it appears that g has a vertical asymptote. Indeed, if we use this slider to change the input values and have the input gets closer and closer to 2 from the right, then right now g is 4, now it's 5, now it's 6. As we get closer and closer to 2, it's now 7, now it's 17, now it's 34, now it's 51, and when I get the input to be 2.01, I get 101. So it definitely seems like the output values are blowing up. They're getting to be very, very large. On the other hand, if I try to approach 2 from the left-hand side, so when a is, say, about 1.5, it's minus 1.16, and we'll keep trying to get closer and closer. So it's at -2, it's at -3 as I get closer. Now it's at -9. Now it's at -13. Now it's at -19. Now it's at -49. If I can get it really close, now it's at -99. So from the left, it also appears that the function outputs are getting big, but in this time they're getting big negative. So in this case, it takes two limits to describe the behavior of g near 2. The limit as x goes to 2 from the left of g of x is equal to -infinity, whereas the limit as x goes to 2 from the right of g of x is equal to +infinity. Once again, these one-sided limits are describing the behavior of g near 2. Now finally, we're going to consider a function h of x equals 3 times sine of 1 over x. So what is this function going to do near x equals 0? What's its behavior near x equals 0? The graph doesn't help that much because the graph should be like a nice line passing through 0, but here it appears to be like a solid, thick thing. What the heck is going on? Well, we could try to investigate it by zooming in. And as we zoom in closer and closer and closer, wow, the lines get closer and closer, but nonetheless, once you get in close enough, it just looks like a solid chunk of blue. This doesn't look like the graph of a function at all. So we'll zoom back out. What we can also do is try plugging in a value a and then seeing what happens to the output h of a as a gets closer to 0. So we move in here and the values, let's see, 2.8 minus 1.5, 7.78, 2.4. I mean, it doesn't seem to be getting close to any one number. Sometimes it's positive, sometimes it's negative. What can we say? This turns out to be an example of a function that's just very poorly behaved. Well, I mean, it's not necessarily poorly behaved, it's very interestingly behaved. And it kind of just goes completely crazy. So in this case, we can say the limit as x goes to 0 of h, the limit as x goes to 0 of h of x does not exist. And again, the limit is describing the behavior of h near x equals 0. In fact, we can go further. We can say that the limit as x goes to 0 from the right or the left of h of x does not exist, because the function is just going completely crazy and is oscillating infinitely many times around 0. Again, the limit, both the two-sided and the one-sided limits are telling that to us. By saying that the limit doesn't exist, it's basically saying something weird is going on. In this case, the function is just zigzagging back and forth wildly, infinitely many times. One final note. I've put a link to all of these Desmos programs on the Blackboard site for this course. So if you want to go ahead, you can change the functions around if you want. You can change the parameters of the slider and investigate limits this way. Feel free.